Okay, so so our goal in this second part, as I told you, is to reduce the space complexity required by 2D range trees for those associated structures. So for the associated structure, we are not going to be using a 2D range tree, but instead priority search tree in such a way that we are going to answer queries of the form like this. From not bounded on one side, report everything until a threshold in the x-coordinate, and out of these, report the ones that are between qy and qy prime. And you want to still be able to do this in OK plus 1 time, or not OK, yeah, actually we don't want to do it now in log n time, because in 2D range tree, you were trying to do it in log n time, because our query time at the end will be log square n plus k time. All right, so we need to be able to perform these queries in log n time in total, just like 2D range trees. And therefore, we are going to replace the 2D range tree with the same log n time. We should be able to answer the same queries in reduced space. Okay, so priority search tree, variations of this exist in literature. Sometimes they're called treeps. A treep is a data structure very similar to this priority search tree, which the term treep is like a mashup of tree and heap. All right, and sometimes they're also called randomized balanced search trees. You build a balanced search tree by assigning random priorities to nodes, which will dictate a certain way to select the center point, and their expected height is log n. But these are just some additional data structures in literature which are related to this priority search trees. But our problem here is to solve queries of this type. Right now, here the way we create a balanced tree from here is like this. So this figure shows how the x-coordinates are used for the heap property. So in terms of the x-coordinates, this tree is a heap. And in terms of the y-coordinates, this tree is like a binary search tree. But we are not using the y-coordinate of 0.5 as a separator. So the y-coordinate is chosen, the key y-coordinate can be chosen arbitrarily. So that's another thing we have in binary search trees. We can choose an arbitrary key value to separate the elements into two. So we choose this y value as the median y-coordinate among the remaining point sets here. So first of all, since P5 has the smallest x-coordinate, it's going to be at the root node. Okay, so we're going to put P5 at the root node. How we are going to divide the remaining points into two sets, that's the freedom heap provides us. You can divide them in any way you like. So just choose a median y-coordinate so that, for example, it may be the median y-coordinate may be P1 or P4 here. So all the way from all the points which have y-coordinates less than or equal to this median coordinate P4's y-coordinate, maybe the median one. Put all of them in the left subtree, put the remaining of them in the right subtree. So by using the median y-coordinate of these remaining points, you guarantee a balanced structure. Okay, and out of these points that you divide into two sets, which one is going to be the root node, again, is determined by the heap property. P3 has the smallest x-coordinate, put it in the root node. Okay, so this way, this priority search tree, as I said, will be heap in terms of the x-coordinate. So we can answer queries like report all of the nodes that are less than, for example, a certain x-coordinate. So we can continue by we can try to report the things here that have smaller than a certain x coordinate, because the entire tree, also all of the subtrees, have the heap property. And it's also a binary search tree. We can do a one-dimensional binary search on this with respect to y coordinates. Since we only want to report things between y and y prime, our algorithm is going to be like this. We are going to search for y and y prime together simultaneously on this, find the place there where we split. So this report in subtree is the place where we are going to replace the entire report subtree routine with the report in subtree, which is going to take into the heap property into account. So these are the shaded trees are all of the report points with y coordinates between qy and qy prime. Okay, because we don't want to report anything else that are not between qy and qy prime. So this is like since it's also like a binary search tree, we treat it as if it's the main part of the algorithm is like a one-dimensional binary search on this tree. But when we report the entire tree, we replace the report entire tree subroutine with this routine that is actually looking at the x coordinates. We don't want to report everything that is in the subtree. We just want to report the ones with x coordinates smaller than qx. So what we are going to do is the smallest x coordinate one is at the root node of the subtree, right? We are going to compare it with qx. If qx is smaller, for example, we are going to report it and look at this left and right subtree. So in terms of reporting the elements in the subtree with smaller than qx x coordinates, we are going to use the technique that I have described here. Okay, or in this example, I gave you an example in which we were reporting points that are less than 6. So we will do the same thing. So if this is like a subtree, and instead of reporting the entire subtree, we are going to say just touch the nodes that are less than qx. So this essentially solves the problem simultaneously. This is a very nice method which is able to solve queries of the type which are not bounded in one side, but up to a certain threshold, and which are bounded in the other attribute between qy and qy prime. We can use this priority search tree to solve this problem. Again, the total running time still will be log square n, but the good thing is that we can achieve log n query time. So such a priority search tree for two-dimensional points, queries in that form will be able to answer them in log n plus k time with ON storage. So its storage is better than 2D range trees by a log n factor less than 2D range trees. Another thing is we can achieve log n query time on this priority search tree without the need for fractional cascading. We don't need fractional cascading. The entire tree, the two-dimensional query we can perform in log n plus k time. All right, but it has to be only queries of that type from some unbounded in one end up to a certain threshold, and the other is a regular bound. Okay, so this is the final thing about this. By using this priority search tree, we can, so this is the final theorem about this first problem, in which we have horizontal or vertical line segments, and we have an orthogonal range query to report the segments that are inside it. So a priority search tree for a set of points in the plane uses ON storage, can be built in ON log n time. Using priority search tree, we can report everything in log n plus k time. So this is actually the theorem about the associated structure of our interval trees. So for the line segment problem, horizontal and vertical line segment problem, we are going to use priority search trees along with interval trees, and the query time, it will be log square n in that case. All right. Now, the final part of today's class is going to now go back to the general, more difficult version of the problem in which we have arbitrarily oriented line segments, and we still want to find the ones that are contained or that are intersected by a query window. Here, the first paragraphs are talking about possibly can be used, for example, interval trees and priority search trees that we have developed in the first two subsections to solve this problem. For example, by converting these arbitrarily oriented line segments into line segments that are horizontal and vertical, like by using their bounding boxes. The thing is that we may have lots of false, if you just intersect the bounding boxes, the fact that the bounding box intersects with the query window does not necessarily mean that the line segment itself is intersecting with the query window is bad news for us, which means that we cannot use this idea because there will be lots of false positives that we report, the bounding box intersecting, but the actual thing does not intersect. Or we can maybe use this to filter out things, but in the worst case, I mean, you can maybe in some randomly distributed line segments, this technique can be used to filter out things that are known to not intersect. For example, if the bounding box doesn't intersect the query window, it's for sure that we can make, this is for certain that the line segment does not intersect the query window. So they can be filtered out. The interval tree along with the priority search tree can be used to filter out certain line segments. But this figure at the bottom shows that it may be possible that you don't filter out any of those lines. So this is the worst case example in which all of the bounding boxes intersect with our query window and actually none of the line segments are intersecting. So in the worst case, we can still try to do ON check for all of these arbitrarily oriented line segments. All right, so basically the final verdict is that we cannot use interval trees or and priority search trees together to solve this more generic problem. Now, we're going to also, the priority search tree query is also not good, because if you look at this part, an arbitrary oriented line segment can intersect the left boundary when the point is outside the query window. So there may be some false positives. There can also be some false negatives, meaning that we deem that our verdict here is that this segment, since its endpoint is outside this query, we say that this is not to be reported. So it's a negative for the priority search tree, but it's actually a positive. As you can see, it intersects the left boundary. Okay, so the priority search tree will not also work. That associated structure will not help us. When the line segments are arbitrarily oriented, we need something else. And that's the place where we are going to treat the problem by using a different approach. This locus approach that this one talks about is like this. We are going to divide our entire solution space into regions, into partitions, and we are going to build a data structure on those partitions. So the idea is this. Let me show you. For example, imagine the locus approach is something like this. Imagine we have some points. If this is my query window, I report these 2 points as a solution, right? If I move the query window a little bit to the right, I still report the same points. Now, actually, if I could have solved the original problem in chapter 5, where we have points and these query rectangles, also with the locus approach saying that in certain regions, so any bounding box within this region where I don't touch the other points, I'm only reporting these 2 points. So if my query was here, okay, actually it's not going to work it like that, right? I mean, it has to, so it has to include this one. So my locus, so how do you define a locus in this case? So what I'm trying to say is that what is the set of, actually we can do that. the set of all the possible rectangles in which only these 2 points are reported. That's the locus of these 2 points. So consider all the queries, rectangular queries, in which the solution is just these two points. Okay, so any query within this partition of the space in which these two are the only, this point and this point are the only two outputs that are going to be reported, actually tells us if your query is in this space, in this solution space, is one of those rectangles. You have to report those. So if we can have these solution spaces, these partitions, nicely organized and nicely queryable, if we can query these in a nice manner, when we have a query, all we need to do is which solution space do you belong to? And if we can find that quickly, we can just report whatever we have in that part of whatever is going to be reported in that solution space. So this is called the locus approach. So if we go back to the problem of line segments, and let's take a look at the one-dimensional case. So look at this one-dimensional case. Any query, look at all the possible QXs we have. For example, from here to here, not including this endpoint here. If my QX is here, I'm still reporting these two line segments. If QX is here, I'm still reporting these two segments. So in the one-dimensional case, the solution space can easily be dividable into partitions such that when the QX, when your query is in that interval, we are going to report this and this as the output. Okay, so the segment tree is based on this idea. We can divide the entire solution space into regions induced by the endpoints of these segments. So each one of those endpoints, as you can see, it's the starting and ending of a partition. So for each of those endpoints, I'm going to use them. If there is no endpoint in a slab, it means that any query within this slab is always going to return these two as the solution. So that's the idea. So if we can build a tree over these, these are by the way called elementary intervals. These are the smallest intervals induced by the endpoints, and which may their size is still linear. They cannot be, since we have 2n endpoints. With 2n endpoints, you can partition the space to at most 2n plus 1 regions, right? Or yeah, something like that. So it's still linear. So this is what we are going to do. Each of these endpoints are going to divide the subspace into regions, and the segment tree that we are going to see in this last section is going to be a balanced tree built on top of these elementary intervals. Okay, now I'm going to talk about what the leaf nodes are and how do we represent those elementary, what kind of elementary intervals we have. So let me copy this here. All right, it worked now. So let me resize a little bit and move to center, flatten my image. All right, now the elementary intervals that I'm going to be describing are of two types. There are intervals which are of length greater than 0. So there are two types of elementary intervals here, with length greater than 0 and with length equal to 0. It's like single points, like endpoints. Endpoints themselves will be one elementary interval, and their length is going to be 0. And they will those endpoints will be the only closed intervals. The other intervals are going to be open intervals. The reason is that at an endpoint, we may have, can you hear me? Because I had a message from WebEx saying the network connection is lost. All right, perfect. Okay, thank you. So here, let me just show you an example. This is not given here, but let's assume we have another segment here. Let's call it S6. All right. Now, since we are doing the locus approach, at the endpoint here, we cannot include, for example, why don't we have intervals that include the endpoints? You may argue that, for example, why does this non-zero intervals are open intervals, the endpoints are not included, zero length intervals are going to be closed intervals. So what we are going to, why do we have these single points as intervals in terms of our elementary intervals, and in terms of this locus approach solution space? How does it differ in solution space? Now I'm going to show you an example. Let's call this new segment segment 6. Okay, I have 5 segments in this example. This is the 6th segment that starts exactly where S1 ends. Now, if I have a query here, what is the result of that query? S1, S2, and S5, right? The query that is here. At this endpoint where S6 starts, the answer changes. If I have a query at exactly this point, what is the result? By the way, what is this? This is S1, this is S2, and S5. Okay, so when the query was here, if this is Q, within this open interval, as you can see, I intersect S1, S2, and S5. If the query was exactly at the endpoint of S1, the answer changes to S1, S6, S2, and S5. And when the query is somewhere inside S6 like this, if this is like this is Q1, this is query 2, this is query 3. So query 1's result is this, query 2's result is this, and query 3's result is S6, S2, S5. Okay, as you can see, the solutions to all these 3 queries are different, and the solution is different at the endpoint if I have these touching line segments. Therefore, these endpoints have to be locuses. They are loci on their own. All right, so therefore the endpoints are treated separately. Now, if you look at this tree, all of the leaf nodes correspond to either one of these 2 types of intervals. For example, the left leaf node here is the interval from -infinity to S1's left endpoint. Let's do left and right to indicate the beginning and ending endpoints of line segments. Look at this interval, which is this looks like, so this is a regular parentheses. Look at this interval from -infinity to S1.L, and it's an open interval. Okay, and this corresponds to this leaf node. This leaf node corresponds to the interval which is closed, which is S1.L and S1.L. Its length is 0. And this interval is another open interval. These are the leaf nodes, and it corresponds to this leaf node. The leaf nodes, all of them, they correspond to elementary intervals. And we build, by just sorting the endpoints from left to right, we get ourselves the elementary intervals. And by using the median of these elementary intervals, we have our root node. And we can build actually from bottom up, we can build a binary search tree on this, a balanced binary search tree on them in a linear time. Okay, but without these labels first. So another important thing of these segment trees are these labels, and these labels are really important. That tells us which solution that locus, a particular locus share. For example, each of the elementary intervals, they are separate loci. All right, so they have separate solutions. The solution is going to be different exactly for that interval, but they share certain segments, and nearby loci also share. For example, this S2, S5 is going to report it in all of these leaf nodes. All of these leaf nodes are going to, whenever your query is in any one of these leaf nodes, you're going to report S2 and S5, right? But if I write all of them in S2 and S5 here, it may be possible that at the leaf nodes, I may have to have ON square labels that I stored in total with all of them. Okay, this S2 and S5 may be repeated a lot in these leaf nodes. So in order to reduce space complexity, the way we are going to do that is we are going to write this label as high as possible in the tree. Our rule will be in this, such that if the interval, which is the union, if the interval of a subtree is the union of all of its elementary intervals, leaf nodes. For example, the interval indicated by this, actually the interval indicated by the root node will be from minus infinity to plus infinity. Okay, so this is our root node. It covers the entire space. The left subtree here covers from minus infinity all the way to this one, which is S2's right endpoint. Okay, so the left subtree is from minus infinity to S2 right. Okay, minus infinity, comma, not parentheses, S2 dot right, which is closed. So we can have, when you get the union of these open and closed intervals, you can get arbitrary intervals like on the left it may be open, on the right it may be closed, right? If you look at this elementary interval, and it's the rightmost node on the left subtree, it's S2's right point. So this one is the interval indicated by the left subtree. So each of these intermediate nodes will indicate they will have a certain interval associated with them. Now the rule that we have is this: if this interval at a subtree is a subset of the segment, which means that if the segment is larger than this interval of this one, it means that all of the elementary nodes inside it should have S2 reported. So we put the label there. And we put the label in such a way that its parent is not a subset of S2. If its parent, if S2 cannot be written here, if we could put S2 here, we wouldn't put it here, okay? And in order to put S2 here, the interval that is indicated by this interval should be a subset of S2. Should be an element, should be included in S2, and in that case it's not the case because S2 starts here, therefore we cannot put S2 here in this label. This is the highest level S2 can be put, and this is how we put the labels on this tree. And after we built first the binary search tree on the elementary intervals, inserting these segments one by one into this tree starting from the root node is not so difficult. In log n time we can actually add these here, and the thing is that at any given level a segments cannot appear more than twice, because it cannot be it cannot include both left and right bars. So for example, when S2 is written here, it will never appear at the levels that are below it. But it may appear multiple times. For example, it may appear on this right subtree at the top node, but on the left subtree it may appear right at another leaf node. So it may occur actually log n times. The label may occur log n times on this tree, and at every level it occurs at most 2 times, since this is a balanced tree with height log n. So each label occurs at most log n times, so which will reduce our O(n) square complexity to n log n if we have this labeling strategy that tries to put the label as high as possible. All right, so this property, like having this attribute as high as possible, which affects all of the leaf nodes, is sometimes called the lazy update in segment trees. So this lazy update is like if a certain thing affects everything underneath, we don't need to push it all the way to the leaf nodes. Just indicate your update here in the intermediate node, and that will be sufficient. It will indicate that's okay. S2 will be a solution. If you have a query anywhere that goes in one of these leaf nodes, S2 should be reported, and this is where you put it. All right. So this is the idea of a segment tree. As you can see, it's entirely different than interval trees. The idea now, we build a tree on these elementary intervals. We first build the binary search tree, and then we label the intermediate nodes with these segments. And at the end, I'm going to erase all these, and now I'm going to show how a query is performed. When we have a query, it's going to we are going to follow the query all the way from the root to some leaf node. For example, if the query follows a certain path like this, wherever it ends, for example, if the query is here, if the query is here, this is my QX. What I will do is very simple. Since each of these intervals also has a key value in terms of x coordinate, for example, if the x coordinate is smaller than S2 endpoint x, I follow the left subtree. If it's larger than S2x, follow the right subtree. So since we have a point query, we are going to follow a unique path from the root node to some particular leaf node, because any point here, if you have any query QX, it will be somewhere between -infinity and infinity, right? So it should be on this x-axis, and since elementary intervals are non-overlapping, they are partitions, it will fall in one of those elementary intervals, which means that you will follow it all the way to some leaf node. Okay, so there will be a path. And while you're walking along this path from the root node to your elementary interval, when you visit the intermediate nodes, whatever data is associated with that leaf nodes, just report that in your output. So anything in this path, when we come to in one of these two elementary intervals, we always report S2, S5, and S1. So when you visit them, these are the segments that is going to be reported. Okay, now it has certain advantages to compared to interval trees. They solve the exact same problem, right? In terms of the one-dimensional problem. In the interval tree was solving the one-dimensional problem where we have these segments and we have a query QX, and our goal is to report the ones that include this QX. It's the same exact problem that the one-dimensional segment tree solves. So what are the pros and cons of interval trees and segment trees? First of all, interval trees are more efficient because they require ON storage. Okay, so that's the pros of interval trees. They require less storage. Segment trees require ON log n storage due to these labels being all over the place. Okay, but at most log n times. So this is the cost we pay for a segment tree. But the biggest advantage of segment tree is we don't need to have an additional associated structure that needs to be processed further. Just think about, in interval trees, we had IMID, okay? At the nodes, the associated structure was IMID. And what we had to do was, we weren't reporting everything in IMID. We had to process them, and in some order, for example, only a subset of IMID was to be reported. So this the biggest advantage of segment trees is that here in the query, the step 1, we don't need to do any additional processing on the data that is stored on the intermediate nodes. We report everything in that intermediate node. Everything has to be reported. Everything is for sure guaranteed to include our query. Now, this is a big advantage, because it means that if I'm going to show you that. So how do we fill in these intermediate nodes? First of all, the creation of intermediate nodes is like this. We build it bottom up. So after we have the leaf nodes, half of them becomes the left subtree, half of them becomes the right subtree. But I'm going to, if you're asking about the labeling of intermediate nodes, I'm going to show you a pseudocode to do that. But if we have the construction of the intermediate nodes is just like we combine two of them, the two of them becomes an intermediate node, these two becomes an intermediate node, then these two intermediate nodes, they are also combined. So we combine them 2 by 2, 2 by 2, like this, and at the end we are going to have ourselves a balanced tree. So every two neighboring elementary nodes, they're combined together to have this level. And after this level, we recursively again do the same thing. Combine the first two to get this one, the next two to get this one, the next two, you combine them to you get this one. So the structure of the tree is built bottom up recursively. But if your question is, how do we label them? How do we intermediate nodes here? Why do I put S5 here? And how do I put S5 here? How do I put S3 here? Is with this code here, insert segment. So after we have the segment tree at the root node, this is one of those segments like S5. We insert each of them one by one. So this bottom-up building can actually be done in O(n) time, but inserting each one of these trees is going to take log n time, and in total I'm going to have, since I'm going to be inserting n segments here into the segment tree to label it, it will be, the construction algorithm will be O(n) log n in total. So this is how it's inserted. For example, when we want to insert S5 into the tree, we do it like this. If you look at the pseudocode, if the interval associated to that intermediate node is a subset of the segment that we are inserting, we just put the label at that node, and then we're finished. We don't go further down. Okay, so if we come to a node, for example S5, and we figure out that this node, the interval indicated by this interval is entirely contained in S5, we just put S5 here and no recursive calls. We just stop here at this point. Okay, and this is what happened actually here in this label S5. When we are inserting it, the interval indicated, so when we are inserting, we come this way, and actually we went both ways. So if we are going to go to the remainder of that pseudocode, and we are going to see that we are actually trying to traverse the entire tree. So how does it work in O log n time? It's I'm going to talk about that. But what happens is that if you look at these recursive calls, which is like two recursive calls, there is no else in this if. So this if and this if, both of them are part of this else. Okay, so actually this else has two statements after it. Okay, it's very bad that they happen to be on two separate pages, but just here it's like this. If the interval is a subset of the segment, then store the label at that intermediate node and stop. This is return from the function. Okay, there is no other statement after that actually. Otherwise, if the interval is not contained entirely in that segment, what we do is we check whether the left child's interval intersects with my segment. Okay, and it may be the case that both left child and right child intersect our segment. So our segment may span part of the left interval and part of the right interval. In that case, I will be calling the insert function recursively for both the left subtree and the right subtree. So as I said, these two ifs are part of this else. Maybe I can show it like this. So when we come to a node and we have some interval segment 2, for example, if this interval indicated by this node is entirely contained in this segment 2, I just put segment 2 and I stop here. If not, I ask this question. If it's not entirely inside S2, does it intersect? Is the left child, is the area interval of the left child intersect with S2? If so, I follow the left child. And I ask the same thing again. This is not a second else. I ask the same question for the right child. If the part of the segment intersects with the right child's interval, follow the right child. So at this point, we can follow both left and right children. Okay? Now, what is the computational complexity of such an algorithm? I mean, look at this. If we go left and right child in the entire tree, imagine this happens to be true, those two ifs in the else part. If it's true for the entire tree, what happens? We traverse the entire tree all the way to the leaf nodes, which results in an ON time, right? If it takes ON time for a single segment, then we are going to have an ON square construction algorithm. So clearly that's not the case. Now, can this happen? Can we have a case where we intersect with both left and right child at every level like this? Imagine a segment 2. Is it possible that, consider this level, is such a configuration possible? Can I call all of these 1, 2, 3, 4, 5, 6, 7, 8 recursive calls that are after this level? The answer is no, because if a segment is intersecting with this right, I mean, if it's intersecting with both and intersecting with these both also, and it's also intersecting with the right segment, what does it tell? Remember that these are elementary intervals that are right next to each other and partition the space. So imagine a segment which intersects with the rightmost one and the leftmost one. What does this imply? It implies that the entire middle part is a subset of the segment, right? So I will not go to the else part. So when I come to this node here, I'm going to store S2 here, and that's it. So this actually implies that at a given level, the number of recursive calls I make is at most 2. I will not be able to if you go left and right at the second level, you cannot go again left and right. The node here, I mean, if you go, so it's like this. Let's get a new one. So if you consider the trees, if you want to go left and you want to go right here, everything in the middle has to be included in the segment. So you're not going to traverse the tree that is in between. You're just going to put your segment 2 at the top here, and that's it. All right. So therefore, since the number of recursive calls you make for a segment at a given depth of the tree is constant, like 2, and since the depth of the tree is log n, it means that inserting a segment into a tree takes log n time. So this algorithm you see here is of O log n complexity. And you do it for every segment one by one. So this insert segment tree function is called for every segment one by one n times. And since each of them takes log n time, in total, in O(n) log n time, we will build this segment tree like this. So this is how we label the nodes, intermediate nodes of the segment tree. All right, I hope it's clear. If you have any questions, please feel free to ask. All right, so after this point, we have a segment tree that is like this. Now, as I said, this is still the one-dimensional problem, but because of the biggest advantage of segment tree, which is this step one. Look at this query algorithm. We report everything. When we traverse a query along the segment tree, we report everything that is stored at an intermediate node. So this gives us a freedom to have any associated structure we want on a secondary attribute. But because we already know they all need to be reported, then if we build as an associated structure on these segments, if I build a structure with respect to their y coordinates, I can immediately extend the segment tree into a two-dimensional problem. Okay, so that's actually the final part that I'm going to talk about here. I'm going to just mention it quickly. What we do is this freedom allows us for and by the way, all the elementary intervals, the segments are going to look like this. Remember, they are arbitrarily oriented, but since we build a segment tree with respect to their endpoints, x coordinates, there will be no x-coordinate endpoint within an interval like this, and the segments that span, that are associated with that elementary interval, can be ordered from top to bottom. There's a total order among them. They are non-intersecting. By the way, this is the place where the first assumption of inputs segments should not intersect works. Okay, if they are intersecting, now we have a problem. If we need to deal with those intersection points, and it will make the problem much more difficult if our input set contains arbitrarily oriented and intersecting segments. Maybe we may first run the algorithm from chapter 2, line segment intersection, to chop the line segments into smaller parts, then run this algorithm. But the problem in this chapter 10 assumes that the input line segments do not intersect, which means that at an elementary interval like this, or at an intermediate node like this, the segments that span the interval are going to be non-intersecting. And non-intersecting implies there is a total order among them from top to bottom or from bottom to top. So we can build a binary search tree on these ordered segments within an interval, and we can use this as the associated structure for the segment tree to extend the problem to the 2D version, and that we can then report all the segments that are between some qy and qy prime values. So this is how it's solved. So this slab, we can query it. So is this, yeah, that's the end of this chapter actually. So the associated structure, the binary search tree on the segments that cross the slab, just like the trapezoidal map chapter. If you remember the trapezoidal map chapter, there was the slab method, which indexed a certain slab by building a binary search tree on the segments that are in the slab. The associated structure is just like that, and it takes log n time to report them. So this step one of the one-dimensional query of segment tree, this step one is replaced. So we replace this step one with a log n search on this additional associated structure with respect to the y coordinates of the segments, or with respect to their order, not the y coordinate, because their y coordinate changes. They don't have, since they're arbitrarily oriented, there is no fixed y coordinate, but you can order them. You can ask the question, is this segment above the other segment or below the other segment? With respect to this comparison function, below above, you can build a binary search tree on those segments, and the step one is replaced with a search in qy prime in that binary search tree, so it takes log n time. So step 1 takes log n time, and since the entire query takes another log n time, this the recursive call, in total we have log square n time n log n storage space. We can solve the general problem of arbitrarily oriented line segments. All right, so that's all I want to talk about this chapter. We have seen 3 data structures: interval trees, priority search trees, and segment trees. And they can be applied to different problems geometrically. Interestingly, segment trees is also very popular in competitive programming, but usually competitive programmers build segment trees on an array of integers, where every integer in an array is an elementary interval, and they build a hierarchical structure on those integer elements with a tree of height log n to perform queries like find the maximum integer in this interval, things like that. So the input in that use of segment tree is not segments. It's an array of integers. So if you're interested, you can also take a look at, you can search for segment trees in like websites like this, for example, segment tree. What was the, yeah, CP algorithms. Yeah, I actually have visited it before. So the CP algorithms is a competitive programming algorithm description website. There's a huge section on segment trees, and if you look at the segment tree that is talked about in this form, the segment tree is something that is built over an array. These are not intervals, these are individual numbers. And the way they built the segment tree is very similar to what we had done in our geometric problem. But it allows certain range updates, range queries. All of them could be answered efficiently with the same ideas provided by the original segment tree. All right. So if you don't have any questions, I'm going to stop here today. We have only 2 topics left until the end of the semester: the robot motion planning, which we are going to talk about next week. We are going to talk about non-point like robots, a polygonal robot with trying to find its way in a 2D map which have polygonal obstacles. Okay, so we'll try to solve this problem, and we'll see Minkowski sums by using the robot's polygon, its area, its shape, how we need to extend the obstacles to see whether the robot can fit in that place or not. Okay, so this is an interesting problem, and we are going to introduce the concept of Minkowski sums. And final week, we are going to talk about visibility graphs again. Again, it's about robot motion planning. This time we'll be interested in shortest paths. All right, this next week is not necessarily the shortest path from some start location to some target location, and we'll see how we can find shortest paths on 2D maps which contains obstacles. All right, so that's it for today. See you all next week. Don't forget to submit your assignment by Sunday midnight. I think it's 27th of December was the deadline for the 3rd assignment. So don't forget to submit your assignment. And that's it for today. See you all next week. Bye-bye.